Okay, let's break apart this formula. It's pretty complicated, and it even gets trickier when you realize this standard deviation of the differences has this formula right here. So what we're doing here, we have paired data. So before and after could be an example, or husband and wife, or something, anything that you can pair the data like this. So the first thing we need to calculate is the differences, and if the problem tells you, you should make sure you pay attention whether it's the second one minus the first one or the first one minus the second one. So I'm just going to do how much we improved from post-test to pre-test. I'm going to take this one minus this one, and I'm going to copy that down. So for example, you see the 45 minus 37 gives us 8, and here we have 53 minus 57, so we get a negative value. The difference is really what we're analyzing then for the rest of the time. So let's get the average. Let me type it over here, average, and this will be the standard deviation of the differences. So we'll type in average and select these. By the way, you could do these by hand or in the TI 84 or 5, whatever you have. When we do standard deviation, we do want to make sure that we get the sample standard deviation. And that's typically the default, but you do want to make sure that you are getting the sample. So this is our sample standard deviation, our average. Let's return to that formula and take a look at what was going on here. So the n would be the number of pairs. We have the standard deviation of the differences now, and then we need our critical t-value. So let's say we're doing a 95% confidence interval. If we go over to stats table here, notice that we do need to know our degrees of freedom here. So it's just like everything's like a one sample t-test. So we'd have 5 data values here. N, I could put that there. Sample size n would equal 5. And so the degrees of freedom would be 1 less than sample size. So if I go over here, degrees of freedom would be 4. And since I want the area in the two tails to total to be 0.05, which is 0.025 in each one, that will give me 95% confidence. If I subtract 95.95 from 1, I would get 0.05. And that gives me 2.776 as my critical t. So call this 2.776. Just throw the degrees of freedom on there to have everything there. And let's return to that formula now. So we basically have everything taken care of here. We have our mean plus or minus. This is our critical t-value, sample standard deviation divided by square root of sample size. So let's get that here. Maybe I'll call this 95% lower, 95% upper. And so this would start with the sample average right there. And then if I'm going to lower, I'm going to subtract that critical t-value that I pulled off of the chart times, this is going to be my standard error here, so I'm going to take standard deviation, that's sample standard deviation, divided by square root of sample size, and that would give me my lower bound on basically how much I've improved. The upper bound, I'm going to do the same thing. In fact, it's going to be so similar that I'm just going to copy that formula right here and then change this to a plus sign. That's really the only difference. So based on these 5 data points, I'd be 95% sure that if this is a random sample of 5, that in general, the students in this class would improve somewhere between actually going down 5 points and going up 13 points. So that's creating that confidence interval. And that is the solution to this one. Let's celebrate.
Yay!